Greetings everyone. Today we'll be looking at divide and conquer method, and before we could proceed with divide and conquer, let's have a small brush up on the recursive functions. What are recursive functions? Recursive functions are self-reference functions, functions that invoke themselves. When do we use such functions? When we can identify that solving the main problem is directly depending on solving the individual subproblems, we go in for recursive functions. What do I mean by that? For example, calculating the factorial of any number, say let's say 5, is dependent on calculating the factorial of 4 because it's 5 into 4 factorial, which is in turn dependent on calculating 3's factorial and so on. We see that the subproblem of 3's factorial and 4's factorial are indeed essential for us to calculate 5's factorial. And the second case wherein calculating the Fibonacci series, we know that from the third term onwards, it is the summation of the first two terms, and if you need the fifth term, you need the summation of the third and the fourth term. So in such cases, recursively solving a problem is intuitive and natural. Now, using recursive functions comes with its own demerits. Recursive functions are function calls, they are function jumps, so naturally stack is being used, and that can be costly because you need to store in the function return pointer and also the local variables in the stack. So stack has been exhaustively used, and recursive function calls can be costlier calls, but solving certain problems is elegant when done using recursive functions. Let us now look at an example of divide and conquer method, but before we could move on to it, let's look at the salient features of a divide and conquer methodology. How do we solve a problem when do we use divide and conquer method to solve any problem? When we identify that there are three ingredients to the problem. First, you divide the problem into subproblems, as we've seen using recursive functions. So most of the divide and conquer problems can be solved using recursive functions, and then you conquer those subproblems individually after dividing them. And finally, once the subproblems are conquered and you have the results, you need to combine them to give the final solution. So this is the methodology in which divide and conquer problems are solved. Let us now look at an example. Let's take the example of a merge sort. Why merge sort? Because it's very easy. We would have done many merge sorters in our day-to-day lives from our childhood. For example, while playing cards, you have two different deck of cards and you merge them based on the numbers. Or maybe if you have a list of strings, you merge them, or if you have pages that are numbered, you merge them based on merge sort when you have your friend alongside. How do you go about doing it? Let us look at the pseudocode and I'll explain it to you. We now have the merge sort algorithm on the board. Let us start with the recursive call. The base condition for this recursive call is that the maximum index, which is indicated by R, should never be lesser than the minimum index indicated by P of the source array called A. So that is the base condition, that is when the function would return. At other cases, we find out the middle index, and using the middle index we pass it to the merge sort as two different subarrays, one from the beginning to the middle, and the next call is from 1 plus the middle till the end. And finally we have the merge step, which I'll explain to you a little later. So this is the recursive call of the merge sort algorithm. Then we have the merge part, so wherein we identify the length of the two subarrays and then assign them, store their values in two different arrays called L and R. So we identify what is the size of the first subarray, that is q minus p plus 1, and then the next subarray, which is r minus q plus 1. This gives the size of the two subarrays. And then we have assigned from the source array, we store the value so that we can park the value somewhere until we merge them. So we have it as a left subarray and the right subarray. So we iteratively assign it to them. Followed by that, we reset the counter values I and j to 0 and ensure that whenever the left subarray's element is minimal, then that should be assigned to the source array, replacing whatever is in place. If not, whatever is there in the right subarray is being replaced, and then the value of the index is incremented to check for the next value. So in this way, you can actually merge the two different subarrays, left and the right subarray, into a single array A. I can figuratively show this to you, how this happens. Let us assume that we have two different elements. These are the two different element arrays. Let's say 2, 3 and 7, and then 1, 4, 5. So this is the left array and this is the right array. So as soon as I start merging this, I see that 2 is greater than 1, and so I put this value in the array A, and then I increment j, and then I find out that 2 is lesser than 4, and so I insert 2 in the main array and then increment I, and I keep doing this continuously until I merge all the elements. Now, to identify the time complexity of the merge sort can be done using the recursive tree method. Recurrence equation of the merge sort algorithm. When the number of elements is 1, the theta value or the order of growth of the function is 1, but in the other cases you have it as twice the times of half of the elements, that is you divide it into two subarrays and the computation time or the complexity time for both of them matters, and you also have an additional complexity for the merge part. So when you write down the recurrence tree or the recursive tree for the merge sort, you get a log n plus 11 levels of Cn, which when computed will result into Cn log n plus Cn. So that can be in turn summarized as the order of growth of the function in the worst case is theta n log n, because we can ignore the lower order or the lower magnitude of n. So for merge sort, the worst case complexity is given by this equation. Thanks for watching.